What if I told you that for over 200 years, one of the most famous scientific laws was wrong? That keeps you grounded was only part of the story? We've all heard the story of Isaac Newton, who discovered gravity when an apple fell on his head. He described gravity as an invisible force pulling objects together, and for centuries that made sense. But then came Albert Einstein, and he shattered that understanding of the universe forever. Isaac Newton, a brilliant English physicist and mathematician, is one of the most influential scientists in history. He revolutionized our understanding of gravity in the 17th century, laying the groundwork for modern physics. Legend has it that Newton's epiphany came as he observed an apple falling from a tree, a moment that would change the course of science forever. This seemingly simple observation sparked a profound insight. The same force that pulls an apple to the ground also governs the motion of the moon around Earth, connecting the heavens and the Earth. Newton formulated his law of universal gravitation, a mathematical masterpiece that describes the attraction between any two objects with mass, no matter how far apart they are. According to Newton, every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them, a concept that was revolutionary at the time. This means that the more massive the objects, the stronger the gravitational attraction between them, a principle that applies universally. Also, the closer the objects, the stronger the pull, illustrating the inverse square law in action. Newton's law elegantly explained why objects fall to the ground, providing a clear understanding of everyday phenomena. It also explained why the moon orbits Earth, a mystery that had puzzled scientists for centuries, and why planets revolve around the sun, unifying the motion of celestial bodies under a single theory. Newton's work was a triumph of science, marking a significant milestone in our quest to understand the universe. It unified celestial and terrestrial phenomena under a single, elegant law, bridging the gap between the heavens and the Earth. His theory of gravity remained unchallenged for over 2 centuries and became a cornerstone of classical physics, influencing countless scientific advancements. Despite its successes, Newton's theory of gravity had limitations. One perplexing aspect was the notion of action at a distance. Newton's law implied that gravity acted instantaneously across vast distances. For example, if the sun were to suddenly disappear, Earth would immediately fly off in a straight line, according to Newton's theory. However, the idea of instantaneous action contradicted the emerging understanding of light and electromagnetism. Scientists had discovered that light, a form of electromagnetic radiation, traveled at a finite speed, not instantaneously. This raised a fundamental question: could gravity be faster than light? Moreover, Newton's theory couldn't fully explain some subtle gravitational phenomena. For instance, the orbit of Mercury, the closest planet to the Sun, exhibited a slight precession that couldn't be accounted for solely by Newton's law. These discrepancies hinted at a deeper, more nuanced understanding of gravity waiting to be discovered. Section 4. Einstein's breakthrough: gravity's dance with space and time. In the early 20th century, a young physicist named Albert Einstein revolutionized our understanding of gravity with his groundbreaking theory of general relativity. Einstein's radical idea was that gravity is not a force acting at a distance, but rather a manifestation of the curvature of space-time itself. He proposed that massive objects, like stars and planets, warp the fabric of space-time around them. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline's surface. Similarly, a massive object creates a dent in space-time. Einstein's theory shattered the Newtonian view of gravity as a simple force. Instead, gravity became an inherent property of the geometry of space-time. Objects don't fall towards each other because of a mysterious force. They follow the curves in space-time created by massive objects. Section 5. Visualizing space-time: the rubber sheet analogy. to understand Einstein's revolutionary concept of warped spacetime. Imagine a stretched rubber sheet representing the fabric of spacetime itself. Now, place a bowling ball, representing a massive object like the sun, right in the center of the sheet. The bowling ball creates a noticeable dip in the rubber sheet, distorting its surface. Now, roll a marble, representing a smaller object like Earth, across the sheet from the edge. As the marble approaches the bowling ball, its path curves due to the dip, and it starts to spiral inward towards the bowling ball. This is a simplified analogy, but it effectively illustrates how space-time curvature dictates the motion of objects in the universe. The marble isn't being pulled by the bowling ball. Rather, it's simply following the curved path created by the bowling ball's presence in the fabric of space-time. Einstein's groundbreaking theory explained that what we perceive as the force of gravity is simply the result of objects following the natural curvature of space-time, shaped by the presence of massive objects like stars and planets. Don't forget to like, share, and subscribe. And join us next time as we dive even deeper into the wonders of the universe.